best of our knowledge with the new emerging topics of AI have been applied for modeling specific issues in relation with components, subsystems, and systems. And this is, in this slide, I would like to remark only some of the main highlights, starting from AI's based modeling framework up to number 6, which is electromagnetic and CFD modeling. In this slide, as you can see, there is a mix of different things. What we would like to remark here is that there has not been a unique path, because the problem is very complex. We have different use cases, and the modeling has become a pillar of different and further stage during these 3 years. Now, in brief, this is one example in which we have obtained not only very, let's say, disruptive scientific results reflected in some Q1 journals, but also from the viewpoint of collaboration. I would like to remark the collaboration, for example, of CSIC with RISE in this paper that's now is drawing a lot of attention of the scientific community. Here there are at the same time in green the techniques and in blue what have been the components that we have been focused on, and some summary on some results. In the modeling, we have not only published in the top journals, but we have also 2 IP results, in this case one trade secret and one registered software that we plan to exploit in short terms.
Sorry, what do I see there? I see graphs without any...
Sorry?
What do I see there? I see graphs without...
Okay, this is the estimation, the models. LSTBN and NBN is the topology of long short-term memory neural networks for predicting the remaining useful life of IGBT. In the middle is an hybrid configuration of LSTBN, multi-layer perceptron, and mixed dynamic networks for predicting remaining useful life of SIG MOFET. And here is the combination of learning, which is a reinforcement learning, and LSTBN, long-term memory for predicting, in this case, the remaining useful life of capacitor. This table is the comparison of different tables. And these results have been published in some journals. Here I'm remarking 2 journals. One is Technologies, and then the second one is IP Play Access. In this paper is the result of collaboration of RISE and CSIC, of course, data and collaboration of also industrial partners such as Favor, but we have leading the writing and the preparation of the manuscript. And we have also these 2 IPR issues, which are the ownership of this IP is CSIC. One is a trade secret, and another one is a registered software. We have some constraints in patenting software, as far as you know, we have problems with patenting software. And the trade secret is a good solution because we don't have to provide any information, to deliver any public information, because we want to preserve it. And we have gone beyond the state of the art in this case, because we are not only applying conventional techniques, we are also using transformer, which is emerging generative AI techniques. And this is something that is now, we are making the first step to create a spin-off in CSIC. We have already 2 startups in CSIC, which we have funded in the last 3 years, and we are creating the 3rd one. I guess that later we have more, we can talk later about this, or tomorrow. This is the second and the 3rd highlights. What I'm highlighting here, once again, is the heterogeneity. I have started by data-driven and system and subsystem viewpoint. Now, this slide is more focused on how we can apply simulation, modeling, combining with simulation for modeling magnetics, for multiphysics simulation of IGBT. Here we can see the simulation. This, once again, the collaboration among partners have been relevant. In this case, the collaboration on PME, Budapest University and ABB. They have been presented in some conferences. There are also collaboration between, in the case of simulations between frenetic and IPT in the use case 1.3, and this is a complete the overall diagram. And these are all the highlights. From the viewpoint of modeling, it's important not only the modeling, it's important the identification of parameters and also optimization. And these are also results related. You can see some of them have been published in top journals. For example, IEEE Journal of American Selected Topics in Power Electronics. This is a result of collaboration of University of Oviedo and the team. There are also conference papers, and once again, optimization as a pillar of modeling and indeed. Last but not least, there are other remarkable results from the viewpoint of modelings, which are near to telomere and electromechanical modeling. Here are some samples, in this case made by EPI Zurich, in which we have seen some characterization of SiC power MOSFETs, also analysis of the switching performance and multi-chip power model with respect to stability. These are the result of collaboration with the team and Infineon. And finally, the role of multiphysics modeling of power models to address electrothermal aspects. Of course, my colleagues are here to enter in details if I require it about this, because I have been the task leader, but of course, the topic is very heterogeneous, it's very wide, and that's all from my side. And the last slide is about KPI and status and BS of the project. I would like to remark that from the viewpoint of modeling, it's rather difficult to identify a KPI with a concrete result, because modeling has been one key pillar and step of the whole project. So all of these are related with the use cases that reflect the main results of the status have been reflected in the use cases results and the validation that we have done. For example, in relation with modeling and decision making, we have done some relevant tests in relation with industrial drivers and Favor, and the use case led by Favor, in which we have obtained relevant KPIs in relation with the reduction of the accuracy for predicting the remaining useful life, and also for reduce the saving cost in relation with reducing the on-scaling stops. So, thank you.
Yeah, thank you for the presentation. Very nice that you provided these examples where you applied the modeling. There's always an issue with the modeling that you have to verify it at the end of the day with some kind of experimental results. I have seen this in the example from ETH Zurich, where we have directly seen the results from the double pulse test measurement and the simulation, where the fit was really very nice. In the other cases, you also have this verification?
Yes, we have been lucky in the sense that when we started, it was challenging, the data availability during the first year. The first year we have employed basically open data sets from NASA, but fortunately the second year of the project we started getting close in collaboration with RISE, with Fagor, with Infineon, and at the end we got data sets from partners. But what is remarkable is that at the end, Fagor developed their own data set that is not public yet, because they need to pass some internal permission to put this data set in public. We are generating surrogate data, synthetic data from the real data, because they don't want to provide their public data for the sake of confidentiality, and we tested it. And for that reason, we received also a good expression of interest, for example, from Expedia, and interested in applying this modeling for predicting the remaining useful life of a GBT in this case. And in the case of Fagor, they are interested in embedding this in their CNC as a way of, as a way of predicting not only the remaining useful life, because the money is not in the prediction, the money is in anticipating. How we can anticipate? The end user can anticipate any failure, because one failure implies that matching stops, the part, the component that is manufactured is broken, and this is a lot of money. So this is what we, and what data said is we have tested it with industrial data, and the results are, and even we have published one paper with rice. We have been in a very big journal, and this is, we are very, indeed we are very, let's say, we're very happy with the cooperation with our colleagues, and this is my personal opinion. Yeah.
Yeah, just as one question, we talked about the modeling of IGBT devices and SIC devices. In your opinion, there is one that is better than one in terms of modeling and matching, or they are similar?
Yes, I think that my colleague put the slide that has been very sincere. In the sense that data heterogeneity, so there is no unique technique to deal with each component. For the reason when I put the comparison, I put different techniques. From the viewpoint of modeling, techniques that provide best results for modeling IGBT was different from SIG. This is basically because data imbalance, data noise is so. So this has been very challenging in the modeling, indeed. For instance, during the aging experiments that have been done in Fagor, the process has been very costly in terms of time, but also later in the test, in terms of post-processing, the variables that we measure. Because it was necessary to measure temperature, current, voltage, and so on. This was a bit very noisy, and this processing was very expensive in terms of time, in terms of